In this video, we'll be discussing how you can predict the relative strength of an acid or base compared to another acid or base. There are three categories of acids that we will be discussing in this class. The first category are oxyacids. Oxyacids are those where the acidic hydrogen, the proton that is being donated, is bound to an oxygen atom. A couple of examples of this are nitric acid, HNO3, hydrosulfuric, H2SO4, and phosphoric, H3PO4. In each case, you have an acidic hydrogen that is bound to an oxygen atom. The bond that is holding the proton on is an oxygen-hydrogen bond. That oxygen is then bound to something that is not carbon. Another type of acid that we will be discussing are binary acids. Those are compounds where the acidic hydrogen is bound to a nonmetal, so bound directly to the nonmetal. So we have bromic acid, HBr, hydrogen sulfide, H2S, and ammonia. In each case, you have the hydrogen that will be donated bound directly to a non-oxygen, non-carbon atom. Right? The last type are our organic acids. These are acids where the acidic hydrogen is part of a COOH group. That is this component here. Right? You have a carbon that is bound to an oxygen that is bound to your acidic hydrogen, but that carbon is also double bound to another oxygen atom. We will talk about electron withdrawing groups and how things like this double bound oxygen pull out electron density, weakening this oxygen-hydrogen bond, making that hydrogen, this one, much more acidic. So in terms of the structure of an acid, in each case you have a hydrogen. Most of the time it's going to be bound to an oxygen atom. Right? The hydrogen-oxygen bond is fairly weak, making it easy for the hydrogen to come off. But what the oxygen is bound to matters. So if we look at an example of chlorous acid, that's HClO2, and compare it to nitrous acid, which is HNO2, the difference between these two molecules is in one we have a chlorine, which is the third most electronegative atom. The other one is a nitrogen, which is less electronegative. So the chlorine is only slightly less electronegative than the oxygen, meaning that the oxygen has a difficult time pulling electron density out of the chlorine. Instead, it gets it from the hydrogen. So that means that the electron density, or the electrons in the bond being shared by the hydrogen and the oxygen atom, spend more of their time around the oxygen in the chlorous acid than they do in the nitrous acid. In nitrous acid, nitrogen is a good bit less electronegative than the oxygen, so the oxygen is able to pull out some of the electron density it needs from this nitrogen, meaning that it doesn't have to pull quite as much from the hydrogen in this bond. And we can see from the Ka, the acid dissociation constant, that in the case of chlorous acid has a much higher Ka value than does the nitrous acid. Right? In chlorous acid, it's 1.1 times 10 to the negative 2, whereas in nitrous acid, it is 4.6 times 10 to the negative 4. So that means that we could expect that the concentration of the hydronium ions, the H3O+, in a solution made from chlorous acid would be significantly higher than in the case of nitrous acid. Hydrofluoric acid would be the H bound to the F. This has a similar strength in terms of acidity to the nitrous acid. It would be a little bit more acidic, but not to a large extent. Then we could look at our various organic acids and compare how the groups attached to that acidic group, the COOH, can affect the acidity of the acidic hydrogen. So we have formic acid, in which the carbonic acid group, or the HCOOH group, is also bound to a hydrogen. We got benzoic acid, where the carboxylic acid, the COOH group is bound to benzene, or acetic acid, which the COOH group is bound to a methyl, CH3. You can see in the case of benzoic acid and acetic acid, the Ka values are fairly similar. Formic acid is a much stronger acid than acetic acid, and as well it's also stronger than benzoic acid. But the three groups have different acidities, and that's based on not just what the hydrogen is bound to, but what is bound to, essentially what is bound to that, right? So whether it's a hydrogen, a benzene, or a methyl group can affect how easy it is to remove this hydrogen, how acidic or how weak the bond is that is holding that hydrogen in place. So essentially, the structure affects the acidity. There are different types of atoms that can be bound to our molecule. We can have what are called electron withdrawing groups. Those are atoms that have high electronegativities, i.e. they pull electron density towards them. You have electron donating groups. Those are groups with low electronegativities or a large amount of electron density in the atoms. Those can both, either electron withdrawing groups or electron donating groups, can influence the strength of an acid. So we could look at CH3COOH versus CF3COOH. In this case, the fluorine here, the three fluorine atoms are pulling a lot of electron density out of the carbon. This carbon is bound to the acidic carbon. And so what you can say is that electron density is being pulled away from that acidic bond, the OH, that's bound to the carbon. And so this one, the CF3COOH, is going to be more acidic than our acetic acid, which is CH3COOH. In this case, the hydrogen has a very similar electronegativity to the carbon, and so it won't really be pulling or pushing too much electron density around. And so the strength of the bond that's holding the acidic hydrogen on, in the case of acetic acid, will be stronger than the bond that's holding on the acidic hydrogen in CF3COOH. We could look at perchloric acid, chloric acid, chlorous acid, and hypochlorous acid. And we will look at examples of these in one of the subsequent slides. The hydrogen is bound to an oxygen. That oxygen, in each case, is bound to chlorine. But the difference between these four oxyacids is what is bound to the thing that is bound to the oxygen, which is bound to the hydrogen. In the case of the hypochlorous acid, there is nothing else bound to the chlorine. In the case of the chlorous acid, we have two oxygens. So we have one oxygen that's holding the hydrogen on, and then another oxygen which is pulling electron density out of the chlorine. In the case of chloric acid, HClO3, you have two additional oxygens which are bound to the chlorine in addition to the oxygen that's also bound to the hydrogen. So that means that this one becomes even more acidic, and then the perchloric acid even more so. We could look at hypochlorous, hypobromous, and hypofluoric acid. Each one of these has a hydrogen that's bound to the oxygen. The oxygen is then bound to the various halides. And in each case, it's what is bound to the oxygen. Well, in the case of the hypofluorous acid, the oxygen is bound to a fluorine, which is the most electronegative. So this one here would be the most acidic. HBRO, which would be a bromine bound to the oxygen, bound to the hydrogen. This would be the least acidic of the group, and HClO, hypochlorous acid, would be in between. There is what we call an inductive effect. The inductive effect is the alteration of the electron density of an atom by another atom or group, one or more bonds removed. We saw this in the case of our organic acids before, when we had the bromic acid versus the acetic acid, where one had C6H6, the bromic acid, bound to the carboxylic acid, the COOH group. versus acetic acid, where it was the CH3 group, the methyl group, that was bound to the carbonic acid, the COOH. The effect of the pulling the electrons away from the bond is what will make it more acidic. Now, the last thing that's going to have an effect is if we start varying the thing that the hydrogen is attached to. So instead of having a hydrogen that's bound to an oxygen atom, if we're comparing our different binary acids, where you have the hydrogen bound to something else, a non-metal, then what it's bound to matters. So you could have think about it in terms of the electronegativity, where you have electron density being pulled out of the hydrogen, but what actually has a larger effect is the size or the radius of the atom that the hydrogen is bound to. We will see how this plays out in just a little bit, but because the iodine in hydroiodic acid, HI, is a lot bigger than the bromine atom in hydrobromic acid, HI, that hydrogen is fairly far removed from the nucleus of the iodine, making it a fairly weak bond. Similarly, H2S, right, the sulfur, is a lot bigger in diameter than the oxygen, making it easier to break an HS bond, a hydrogen-sulfur bond, than it is to break a hydrogen-oxygen bond. So if we're looking at our various oxyacids, and we're looking at the perchloric, chloric, chlorous, and hypochloric acids, what we're interested in is looking to see where the electron density is. So in each case, the key component is the same, right? Your hydrogen is bound to an oxygen, which is bound to a chlorine atom, right? It's the same in all cases. So the first group is the same, but the difference is what is bound to that chlorine. So in the case of the hypochlorous acid, there is nothing else around it. In the case of the chlorous acid, you have an additional oxygen group that's bound to the chlorine. This oxygen group is going to be pulling electron density towards it. Right? So if it's pulling electron density towards it, it's pulling electron density from the chlorine. That chlorine needs to get it, so it's going to be pulling a little bit stronger on the electron density away from the acidic oxygen. Right? So that will weaken this the hydrogen-oxygen bond, because the oxygen, this oxygen here, will be pulling electron density towards it. If we add on an additional oxygen, right, an additional oxygen, so now we have two, you have two things that are pulling electron density away from the chlorine. The chlorine will now pull even stronger on the electron density coming out of the oxygen, and that oxygen will in turn pull even more electron density out of the hydrogen, weakening the oxygen-hydrogen bond, making this hydrogen more acidic than the case of chlorous acid. Then in the last case, the perchloric acid, where we have three oxygens in addition to the one that's bound to the hydrogen, you have a lot of electron density being pulled out of the chlorine, right? Being pulled towards each one of those oxygens, which means that the chlorine-oxygen bond here, you're going to have a lot of electron density being pulled out of the oxygen, which means that the oxygen is going to have to pull a large portion of electron density out of the hydrogen, making the bond holding this hydrogen here on very weak. So in terms of the relative strengths of the acid, the perchloric acid is the strongest acid. The chloric acid is the second strongest. The chlorous acid is the third. And then the hypochlorous acid is number 4. Right? An easy way of comparing the relative strengths of your oxyacids, if the central atom, in this case chlorine, is the same in each, then whichever one of your oxyacids have more oxygen has more electron density being pulled out of that central atom, making it more acidic. In the case of our binary acids, HF, HCl, HBr, and HI, as well as like H2S versus H2O, H2SE, or H3N, right? What really matters is the size of the bond. The larger the bond is, the easier it is for the bond to break. So, in the case of like HF versus HCl, the general trend in atomic radius increases as you go down and increases as you go to the left. But the atomic radius increases far more going down between two cells versus going to the left. By that, I mean that the difference in atomic radius between fluorine and chlorine is significantly more than the difference between fluorine and oxygen. So, if we compare the relative strengths of HF, so we have a hydrogen bound to a fluorine atom, right, versus HCl, the bond length that's holding the acidic hydrogen on for HCl is longer just because the radius of the chlorine atom is so much more. Then we can compare that to HBr. Bromine atoms are a lot bigger than chlorine. And then the HI bond is the longest yet, making it the weakest. So because the hydrogen that's attached to the iodine in hydroiodic acid is so far away from the iodine, it's very easy to break this bond, giving you the H plus the I minus. Right? The bond is very weak, so it's easy to break. And the reason that it's weak is because it is very long. So because the bond is long, it is weak, it is easy to break, making HI the strongest of the four acids. So in terms of strength, HI is the strongest, HBr is the second, HCl is the third, and HF is the fourth. The general takeaway when you're trying to compare various molecules to determine which one is the most acidic, focus on the strength of the bond holding the acidic hydrogen onto the molecule. When comparing molecules, look for the first difference and ask, will that difference pull electron density away from the acidic bond or push electron density towards it? And the last one is, if we're comparing two atoms together, what is the size of the bond holding the acidic hydrogen on? The longer the bond is, the weaker it is.